Dear students, in today's class, let us find the solutions for the numerical problems which appeared in the March 2014 annual examination. Let's have a look on the very first problem, that is, in a parallel plate capacitor with the air between the plates, each plate has an area of 6 into 10 to the power of minus 3 meter square and the distance between the plates is 3 millimeter. Calculate the capacitance of the capacitor. If the capacitor is connected to 100 volt supply, what is the charge on each plate of the capacitor? And they have given absolute permittivity of a free space is equals to 8.85 into 10 to the power of minus 12 force per meter. Here we need to find out two parameters. One is capacitance of the capacitor, another one is charge on each plate of the capacitor when it is connected to 100 volt supply. So let me write first given data. The given data is that is area of cross section of each plate as in the problem, that is area of cross section of the each plate is 6 into 10 to the power minus 3 meter square. Next area, so distance between the two plates is a 3 millimeter, that is distance between the plates is 3 millimeter. Milli is nothing but 10 to the power minus 3 meter. And we need to calculate the capacitance of the capacitor. One more information there again, that is permittivity of the free space, that is equals to 8.85 times 10 to the power minus 12 force per meter. We know that the capacitance of the capacitor is given by C is equals to epsilon naught A divided by D. Just on substituting, you can get the capacitance of the capacitor. So now epsilon naught value is 8.85 into 10 to the power minus 12, and the area of the each plate 6 into 10 to the power minus 3 divided by the distance between the two plates is 3 into 10 to the power minus 3. So this 10 to the power minus 3, 10 to the power minus 3 get cancelled, and 3 1 ja, 3 2 ja, and 8.85 into 2, this is equals to C equals to, we can get 17.71 into 10 to the power minus 12 farad, or else we could write C equals to 17.71 picofarad. You could write 17.71 picofarad is the capacitance of the capacitor. Now one more thing we need to find out, that is the charge on each plate of the capacitor when it is subjected to the 100 volt supply. So we know that the charge on each plate of the capacitor equals to C capacitance on the capacitor times the potential difference between the two plates, because we know that the capacitance of the capacitor is defined as the charge on the capacitor to the potential difference between the plates of the capacitor. So therefore we can write Q equals to CV. So now Q equals to C, just now we found that is 17.71 into 10 to the power minus 12, and the voltage is 100 volt, that is 10 to the power 2. So therefore Q equals to 17.71 into 10 to the power 10 power minus 10. So minus 10 coulomb, or else we could write 1.771 into 10 to the power minus 9 coulomb. So that is Q equals to 1.771 nanocoulomb, that is plus 1.77 nanocoulomb is present on one plate of the capacitor, another minus 1.77 nanocoulomb is present on another plate of the capacitor. So this is the charge stored on the plates of the capacitor, and this is the capacitance of the parallel plate capacitor. Okay, let's have the next problem, that is A battery of internal resistance 3 ohm is connected to 20 ohm resistor and the potential difference across the resistor is 10 volt. If another resistor of 30 ohm is connected in series with the first resistor and the battery again connected to the combination, calculate the EMF and the terminal potential difference across the combination. So let's have a look on the given data first. The internal resistance of the given cell is equals to 3 ohm and the first resistor, that is R1, equals to 20 ohm. Across the R1 there is a potential difference of 10 volt. Let me write V is equals to 10 volt. There is only one resistor. If another resistor of 30 ohm is connected, that is R2 equals to 30 ohm. If it is connected in series with the first resistor, the battery again connected to the combination, we need to calculate the EMF of the two cells. So we know that whenever the cell is connected to the external resistance, the current flowing through the circuit is given by I equals to E divided by capital R, that is external resistance, plus small r, that is internal resistance. But we don't know the current flowing through the circuit, so therefore I am expressing current flowing through the circuit as like this, that is V divided by R by using Ohm's law, because we know that Ohm's law is V equals to IR, so therefore we can write I in terms of V and R. Now V equals to E divided by R plus R. So now we want to find out EMF of the cell, so therefore let me make E as a subject formula here, so therefore we will get E is equals to V of R plus R divided by capital R. So on substituting the values, that is E equals to, the V equals E equals 10 of capital R is 20 ohm, small r, that is internal resistance is 3 ohm, divided by capital R 20 ohm. So this will become 230 divided by 20 and E equals to, so we will get 230 divided by 20, that is equals to 11.5 volt is the EMF of the shell. Now we need to find out the terminal potential difference across the combination. What is the terminal potential difference across the combination? They are connected in series, so therefore the effective resistance of these two will be equals to R1 plus R2, that is 30 plus 20 is 50 ohm. We need to find out now potential difference across the combination, that is RS, across the effective resistance. So we have seen that there is a battery which is again connected, so therefore we can write the current flowing through the circuit is equals to E divided by external resistance plus internal resistance. Here we connected it to the combination, for that is instead of taking only resistance we can take effective resistance. Now I can be written in terms of terminal potential difference divided by the effective resistance V dash divided by RS. This is equals to E divided by RS plus R. Now here we need to find out terminal potential difference across the combination, that is V dash. So therefore let me make V dash as a subject formula, that is E RS divided by RS plus R. So therefore V dash is equals to, here E equals to, just now we found that 11.5 into RS is 50 ohm divided by RS equals to 50 plus internal resistance. Now from simplifying you will get V dash is equals to 11.5 into 50 divided by 53. So we will get 10.849 volt. This is the terminal potential difference across the combination. Okay. Let's have a next one, that is calculate a resonant frequency and Q factor of a series LCR circuit containing a pure inductor of inductance 3 Henry, capacitor of capacitance 27 microfarad, and resistor of resistance 7.4 ohm. Here we have the pure inductor of inductance, that is L is equals to, here L is equals to 3 Henry we have, and capacitance of capacitor, that is C is equals to 27 microfarad, and resistor of resistance, that is R is equals to 7.4 ohm. So we need to find out resonant frequency. We have seen that the resonant frequency is equals to 1 divided by 2 pi square root of LC. We know that at resonance the inductive reactance is equals to capacitive reactance. By using that we can get F naught equals to 1 by 2 pi root LC. So on substituting the data, that is 1 divided by 2 times the pi value is 3.142 root L is equals to 3 Henry, and the capacitance of capacitor is 27 microfarad, 10 to the power of minus 6. So this is equals to 1 divided by 2 into 3.142 is 6.284 root 81 into 10 to the power of minus 6. Now this is equals to 1 divided by 6.284 into root 81 is 9, and root 10 to the power of minus 6 is 10 to the power of minus 3. And when 10 to the power of minus 3 comes to the numerator, it will become plus 3. So therefore F naught is equals to, that is resonant frequency, F naught is equals to 1000 divided by 6.284 times 9. This is equals to F naught equals to, that is 1000 divided by 56.5. So therefore we will get F naught is equals to 17.69 Hertz. This is what the resonant frequency of a series LCR circuit. Now we need to find out the Q factor. We know that the Q factor is equals to angular resonant frequency into L divided by R, omega naught L divided by R. On substituting, that is omega naught is nothing but 2 pi F naught L divided by R. Now let me substitute the values, that is 2 pi is 3.142, F naught is, just now we found that 17.69 into L, that is 3 Henry, divided by resistance. Resistance is equals to 7.4. On simplifying, you will get Q is equals to 45. Q is equals to 45. This is the thing you need to keep in mind. So we found Q factor as well as resonant factor. Okay. Okay, let's have a next problem. That is fourth problem. Two lenses of focal length 0.20 meter and 0.30 meter are kept in contact. Find the focal length of the combination and calculate powers of two lenses under the combination. Here the focal length of the individual lenses can be written like this, that is f1 is equals to 0.2 meter and f2 equals to 0.3 meter. f1 is 0.2 and f2 is 0.3 meter they are given. So whenever the two lenses are connected or bring them in contact, or whenever we keep them in contact, at that time the effective or else the focal length of the combination can be written like this, that is f1 f2 divided by f1 plus f2. Okay. Now on substituting the values, that is f1 is 0.2, f2 is 0.3 divided by F1 plus F2, 0.2 plus 0.3. Now 0.2 into 0.3 is 0.06 divided by 0.2 plus 0.5 is 0.2 plus 0.3 is 0.5. So on simplifying, we will get 0.12 meter. That is the focal length of the combination. The focal length of the combination of these two lenses is equals to 0.12 meter. Now let us find out the power of the two lenses. So we know that power is equal to the reciprocal of its focal length. So power of the first lens is equal to the reciprocal of the focal length of the first lens. So therefore power of the first lens is equals to 1 divided by 0.2. So this is nothing but P1 is equals to 0, sorry, P1 is equals to 5 dioptry. In the same way, P2 is equals to 1 divided by F2. That is P2 equals to 1 by 0.3. This is equals to 3.33. 1 by 0.3 is 3.333 will come. That is P2 equals to 3.33 dioptry. So these are the powers of the two lenses. So, and we need to find out power of the combination also. So power of the combination is given by sum of the powers of the individual lenses, that is P1 plus P2. We have two lenses here, so therefore P1 plus P2. Now P1 P is equals to 5 dioptry plus 3.33. This is equals to 8.33 dioptry. Okay, this is power of the combination and power of the first lens, second lens, and the focal length of the combination of the two lenses. Okay, so let's have a last problem, that is calculate the binding energy and binding energy per nucleon in mega electron volt of nitrogen nucleus from the following data. Mass of the proton they have given, that is mass of the proton MP they have given, as well as mass of the neutron, in the same way mass, actual mass of the nucleus, that is nitrogen nucleus they have given. Now to find out the binding energy, first we need to find out the mass defect, because the binding energy comes from the mass defect. So we know that the mass defect is, nothing but it is the difference between the masses of the nucleons and actual mass of the nucleus. That is, mass of the nucleus is ZMP plus A minus ZMN minus actual mass of the nucleus. So this is what masses of the nucleons and actual mass of the nucleus. That is what delta M is equals to Z. How much Z we have here? So we can see the Z equals to 7. Here the E in the nitrogen nucleus, the mass number is 14 and atomic number, that is 7 is, Z is equals to 7, and the number of neutrons, that is A minus Z, is equals to 7 we can see. So therefore here Z equals to 7. Mass of the proton is here 1.00783 plus A minus Z is also 7, that is mass of the neutrons, number of neutrons. Next, mass of the neutron is 1.00867 minus actual mass of the nucleus. Actual mass of the nucleus is 14.00307. Now delta M is equals to 7 into 1.00783 plus 7 into 1.00869. If you calculate this, you will come up with the number 14.11172 minus, here we have 14.00307. 307. So mass defect is equals to 0.10872 U. This is the thing you need to give. Mass defect is 0. This much we got. Now we know that for 1 U, for one atomic mass unit, binding energy is equals to 931.5 mega electron volt. And for delta m u, that is for delta m, binding energy can be written like that. Binding energy is equals to delta m times the 931.5 mega electron volt. Now just substitute the mass defect what we found just now, that is 0.10872. This one has substituted, that is 0.10872 times 931.5 mega electron volt, and this is equals to, that is binding energy is equals to 101. So on multiplying these two, we will get 101.273 mega electron volt. So therefore binding energy is equals to, binding energy of the nucleus is equals to how much? 101.273 mega electron volt. And one more parameter we need to find out in this question, that is binding energy per nucleon. Binding energy per nucleon is also called as specific binding energy. What it is called as? Specific binding energy. See, specific binding energy is nothing but binding energy per nucleon. So specific binding energy is equals to binding energy per mass number. So here binding energy is 101.273 mega electron volt divided by the mass number is 14. So therefore it will become 101.273 divided by 14 is equals to 7.231 mega electron volt. This is specific binding energy. So specific binding energy is this much. Binding energy per nucleus. So therefore specific binding energy is equals to how much? 7.231 mega electron volt. So this is the solution for this last problem. So these are the questions appeared in the March 2014 annual examination. Okay, thank you. Thanks for watching.